Okay, great. Can you see my screen all right? Good,
Yeah.
Good. And you can hear me okay, which I'm assuming is a yes. Great, okay. I will get going. So, welcome everyone to the 6th Rust Cryptography Interest Group Sync-up call. My name is Ernest and I'm here from the DevX initiative. And very excited to have everyone here for our 6th one of these. It's been like crazy to think that we've done 6 of these already. The year has gone so fast. Just really excited to be here and share some of this stuff with this topic with you. So I'm just going to give a quick opening address for anybody who may be here for the first time. I know it's a lot of regulars here, but I'll just whiz through this really quickly. So for anyone who may be here for the first time, the Rust Cryptography Interest Group serves as a forum and the roundtable for Rust developers interested in cryptography. The purpose of this call and this roundtable is to foster a dialogue within the Rust cryptography ecosystem. This isn't a showcase for your individual projects, or it's not like something to kind of shill what you're doing per se. It's about the bigger picture of Rust crypto in general. The focus is to explore the current Rust cryptography landscape and mainly diagnose what is needed, to understand what community resources are missing, and to figure out what we can do to make cryptography in Rust better. This, the Rust Cryptography Interest Group was inspired and is a collaboration with Tony and Concordium through the DevX initiative, which I represent. And if you could check these guys out to find out more about the DevX initiative and Concordium, that would be great. We also want to announce from the DevX initiative a sponsorship program that we have launched as a part of the whole initiative. So the DevX initiative isn't just this, it's about a holistic offering to help the Rust community at large. We also partner to help the Rust formal verification interest group as well. And we have announced a sponsorship program for maintainers of the Rust ecosystem. You can read a lot more about it if you go to our Twitter, so I won't go on too much about it here, but we're very excited about this because this is a very important part of what we want to do to make Rust better. Concordium and through the DevX initiative believes that the people who benefit the most from a lot of people who maintain the Rust ecosystem should also benefit as well. So that's why they've endowed the DevX initiative with $100,000 to give out through GitHub sponsors to help people. Very similar to what Embark do, very similar to what Discord have done for Tokyo and things like that. So you'll hear more about that coming soon. We've already started sponsoring Mara and Josh, and we're going to be working with them to identify other maintainers of infrastructural stuff in Rust who need support and sponsorship. But as I said, you can find out more about it at the DevX initiative on Twitter. There's a whole press release and a blog post about it there. Again, this community is a collaboration between Rust Crypto.org and the DevX initiative. And again, it's amazing to partner with incredible individuals like Tony, Rich, and Diego. And please follow them on Twitter as well. Tony, do you want to say a quick hi? Again, it's a lot of friendly faces here, but if you want to just say a quick hello and introduce yourself as a co-host. Same thing for you, Diego and Rich, and then we can move on from there.
Yeah, sure. So I'm Tony Arcieri. I do a lot of open source work as part of the Rust Crypto GitHub organization. Maintain hundreds of crates implementing various cryptographic algorithms in pure Rust. They're trying to build a good Rust cryptography ecosystem.
Great, thank you very much. Diego, do you want to say a quick hi?
Yes, I hope you can hear me. I'm
Yes, we
Diego
can hear you.
Aranha. So I'm professor at the Arhus University. I work at the crypto group here doing cryptographic engineering. I'm also author of the Relic library that some of you might use or hate. And as I said multiple times, I'm trying to graduate from mostly C programmer or direct to assembly implementation person to a Rust programmer. So participating in this call is part of that process.
Great. And Rich, if you want to say a quick hello.
Sure. Hi, Rich. I work at Akamai. I worked for far too many years on OpenSSL, and I'm paying for my sins by trying to help Akamai endorse and use memory safety.
Amazing. Thank you. Just a couple of points of code of conduct. The RCIG follows the Berlin Code of Conduct, the Rust Code of Conduct. Just some really simple, decent human being stuff. We do want to foster debate and robust dialogue, but it just has to be done within a framework of respect and in a framework of kindness and openness and inclusion. So yeah, just some really simple things here about just how we interact with each other on the call. And the etiquette for asking questions. So if I could ask for everyone apart from the host to have their cameras switched off. Hey, Jethro, if you could ask for everyone's cameras to be switched off, that'd be great, because that's part of the process. So taking this etiquette from Nico Matsakis at AWS Amazon, please keep your video switched off. And when you want to indicate that you want to ask a question or say something, then you can switch it on. And that will indicate that you want to say something. If you want to make a follow-up point, you can keep your video switched on. If you don't have a camera on your laptop, you can still use the Zoom hand raise feature. And if you don't want to do that, you can just place your question in chat, and I will scan through the chat for those salient points, for those questions to ask. But priority will be given in a tiering from people who switch on their camera, and then people who use the Zoom hand raising phase, and then people who just ask questions in the chat. So that's just what we want to frame as a protocol and etiquette for asking questions. Thank you very much for understanding. Great. So for today, our agenda, you've just had the opening address from me. I'm going to give a quick recap on what we covered, because we didn't have a call in October. Our last call was in September, and we'll have a quick recap of that. And then we'll have the opening question around what we are trying to discuss on this call, which is some of the code gen issues with LLVM. So that could be quite a spicy topic. And we're also going to get into inline assembly being stable, which is going to be quite exciting, and focusing on what that means for cryptographers in Rust. There's been a lot of discussion previously, if you've watched some of these previous calls on YouTube, about like how we can get some things stable in constant time. And we're going to discuss what having inline assembly could do for that as well. And then we'll have some closing remarks, and then hopefully carry on the discourse from there through the rest of your in your own time. So I'll start with a very quick recap. Last in September, we had a really good call. We had Nico join us from the language team. I mean, everyone knows Nico. And we actually discussed some of the issues that we've been wrestling with. We have a coordination repo on GitHub where we list out a lot of issues that people have identified from us in a community. And if we look at issue number 55, could someone remind me what issue number 55 was from when we discussed that? It was some compiler issues that we spoke about, right, Tony?
Yeah, probably guess what it is, but let me double check. I think this is probably the constant time code generation, right?
Yes, yes,
yeah.
which has been one of the sticklers that we've been wrestling with. It was a really, really positive call. We had a lot of people kind of chime in on some of their own experiences. And what we ended up with was actually 3 actionables that we wanted to take forward to try and actually make it not just a moan fest where we're just moaning about things, but we're also actually kind of working together as a community to get some stuff done. The 2 main things that we identified that we wanted to do to kind of take some next steps forward was to create a sort of questionnaire where people can share some of their experiences and really kind of home in on some specific points and specific gripes that we can use to then take back to the compiler team, so that we can kind of make a step forward with things. And as a follow-on from that, we also discussed the possibility of a focus group where it'll be a call like this, but with less people, maybe 3 to 5 individuals who want to give some direct feedback to individuals in the compiler team as well, so that we can kind of get some things communicated from our end for what we want to see make our lives easier in the cryptography domain. We also wanted to extend that further by trying to actually reach out to some LLVM folks, but that's a bit out of the scope for now. One of the things that we're going to focus on is just crafting this questionnaire, and then focusing on, sorting out the focus group for that as well. We will take some hands to see if anybody wants to help craft some of the questions, and then we can also talk about how we will disseminate that questionnaire to get as much feedback as possible before homing in on that focus group as well. So there's lots going on, lots to still be done before the end of the year. And yeah, it's just really, really, really exciting times. Diego, Tony, how do you guys feel about where we left things prior? And it's kind of been a rolling conversation that we've had since we've begun this, right? Where do you think we need to kind of head forward with that? Some of the things that we've discussed. Rich, please feel free to chime in as well. Diego, did you want to start?
So I wasn't in the previous call, but I listened to it this afternoon, and I think the action points make complete sense because we have all different requirements. Actually, the issue 55 thread collects a whole bunch of interesting things that some of which I wasn't even aware of when they deal with LLVM. And so the problem is harder than I thought at first. I thought that, well, having a secret type is reasonable. It's something that at the Hex workshop we have discussed multiple times in multiple years. And we all wondered why not enough progress was made in that direction. And the reason is simple, right? The problem is harder than it looks at first sight.
Yeah. Tony, do you have any points on that? I mean, you've been intimately, just to say, you've been dealing with this for a while, and it's been something that's been on your radar for a while as well. How do you think about the path that we've chosen forward to move forward, and any other kind of points from the last call that you?
Yeah, I mean, I feel this is an area where like there's been a ton of discussion and not really any like concrete actionable things. Which is why I thought inline assembly is so exciting. So kind of the general problem is for anything you're writing at a high level, right? Anything you're writing in pure Rust, there's practically no way to get guarantees around things like constant time operation, right? So that's kind of some of the stuff we were discussing with Nico is like, what could we possibly do, right? We had discussed like showing off optimizations at the levels of individual functions.
Yes,
that seems like a bit of a pie in the sky idea, and I'm not sure it's actually sufficient. So yeah, I mean, even with all the optimizations off, LLVM still will do this sort of rewriting. There's some things that are just like complete showstoppers. Like there is an optimization pass that will take constant time move, like CMove operations, if they're inside of the body of a loop, which is what they almost always are with cryptography. it'll turn those nice constant time instructions into branches. So yeah, so it's been this kind of like very frustrating thing. Like the other pie in the sky thing was what Diego mentioned, this idea of adding types to LLVM itself that are designed to respect constant time properties throughout the entire LLVM optimizer. So there are people like Chandler Carruth at Google who wanted to do a project for this. And we discussed a lot at Hacks. To my knowledge, there's still some sort of internal project at Google, but they were supposed to make it public and they haven't. So it's been this big frustrating thing, but I think finally with inline assembly, to my understanding, this is like stuff I want to ask among you about, but with inline assembly, you get this sort of black box. I mean, so you're giving up this like idea of like, we want to write portable pure Rust code, but with the inline assembly, you get this little black box where you can stick in these very specific instructions. And as far as I understand, LLVM will not futz with them and try to remove them or rewrite them as branches and that kind of thing. So I would personally love to know more about if that's actually the case. That's kind of my understanding talking to people, but if we have that, we can kind of build little assembly-based primitives that will actually use the correct instructions for constant time operation. So I'm very excited about inline assembly being stabilized. I guess the one other piece of Rust news that's kind of interesting from a cryptography perspective is there's been this whole portable SIMD project.
Yes, I was just about to mention that. Yep. Thank you for reminding me. Yes.
Yeah. So that got merged into the nightly compiler. And that's super exciting for some of our Rust crypto projects where we maintain like multiple architecture specific SIMD backends for algorithms like say CHA-20 or Blake 2 or something like that, Poly 1305. So instead of having these like architecture by architecture SIMD backends, we could hopefully just write a portable one that'll work on any architecture that supports the portable SIMD. So it's pretty exciting developments in Rust recently, I would say.
Yes, that's great to hear. And you almost answered the kind of the question that I wanted to open that the inline assembly aspect with, which is like, what does inline assembly offer Rust crypto or Rust cryptographers now that it's stable? You know, and you made some great points about that.
Yep. So I mentioned cmove. It's a conditional move instruction. You have two registers. You're like, depending on the value of this third register, like move either A or B, right? So that is a good thing, a good foundational thing to build constant time code on. Intel says that my understanding is Intel says cmove is constant time on pretty much every extant Intel CPU with maybe one exception or something, but it's one of these few reliable things. I think the other one that's been like really frustrating for a lot of Rust developers, including I think Jethro, talked a bunch of these issues, and Pratyush has also encountered this, is there are instructions for doing kind of like arbitrary precision arithmetic. Most notably ADX and molx do like adds and multiplies and won't clobber the CPU's flags. So if you use these instructions, you can get instruction level parallelism doing these kind of big num operations. And that's all great, except even though there are wrappers, there are like core arch kind of intrinsic wrappers for these, they don't actually work and they don't generate the right instructions because LLVM doesn't support them. Huge rabbit hole of a big bug that's like, it goes all the way from Rust to LLVM to where like you cannot get it to emit these instructions. And then we've just recently been playing with inline assembly, and so far, I'm not really sure if it's sound, but we've gotten with inline assembly, we've gotten kind of some of these like add carry chains and multiplies to compose and emit what appears to be the right instructions. So I think that's pretty exciting. And yeah, as I see in the chat, there's a mention of subtle. Yes, so this is actually one of the other outcomes we had with Chandler, which is using inline assembly. Yeah, you can create a sort of like value optimization barrier with an LLVM that will prevent its optimizer from kind of seeing through that and create this sort of black box abstraction for creates like subtle, which would be pretty interesting, I think.
Great. Yes. Hi, Jethro. Very, very great to have you here. We're very excited to have you here. You're one of the people that we really wanted to have. So it'd be great to have you share some of your thoughts and feelings on inline assembly and what it offers to Rust Crypto.
Oh, sure. Yeah, I just wanted to chime in on what Tony was saying regarding the MolX instruction. It's not just that LLVM is not emitting the right instruction, but even if it would, right, their optimizer just doesn't know how to handle the flags properly. So any kind of optimization you were hoping to get from using that intrinsic doesn't even work. Yeah. Yeah, I guess Tony asked me to talk a bit about inline assembly and crypto, but to be honest, except for the MolX thing that we just mentioned, the intrinsics have been pretty good for me. Of course, yeah, if you want constant time, it's difficult to prove that. But,
yeah. So how's your experience been from using it in nightly and coming now that it's stable from a syntactic level and seeing it evolve from that time?
Yeah, so like 2 years ago or so before, right? The syntax was very similar to what we were seeing in GCC,
yes.
Where the way you had to specify registers and things like that. So the new syntax is so much better, a lot easier to read, to verify, to audit. But I mean, it's pretty straightforward now. You write some assembly and it works.
Great. Okay, that's really cool to hear. Anybody else? It's now open to anybody else who wants to chime in on their experience coming from where we were to where we are now. Who's had experience with the journey of inline assembly from its time in nightly and even before. Okay, no worries.
Maybe I can say something from my C experience, which is not the same, of course, but one thing that Jethro and others have mentioned already is I never understood why this intrinsics for instruction-specific intrinsics never worked as expected on most compilers, right? Because that this would be, I'm not a compiler person, so that my take might be completely stupid, but it would be a middle ground solution, right? The inline assembly is, of course, you get guarantees because you're writing directly in assembly. The high level version of the code, of course, you have no guarantees because the compiler will do that. When you have instruction level intrinsics, you are in between that. Those intrinsics will encode just one instruction, and you could even, I understand, if the compiler supports it properly in Rust, you could even use that on safe code because there would be an abstraction around that instruction that would not break guarantees that you get with inline assembly, while being able to do things like add with carry or addx or mulx. What's so hard about that? Can anyone chime in and give a reason that's
yeah, so the main optimization problem there is that for let's see, it's add cx and add ox, right, which put the carry bit in a different flag, and LLVM doesn't actually track every flag individually when it's emitting code. So it just sees, okay, this instruction touches flags, right? So it's not able to reason about the data flow through the carry bit and the overflow bit separately. And that's why it's not able to do any optimizations when you were doing that.
Yeah, I'd say kind of the flip side for intrinsics is, when you're talking about having safe APIs, so this is kind of what that portable SIMD work is doing, right? So there's already all these architecture-specific intrinsics that are in like Core Arch for doing things like SIMD XOR, SIMD add, like SIMD bitwise operations, right? So what they've done is take those. They're unsafe, but for the most part, they're like safe, right? They're they're not going to do anything that isn't memory safe. There are some of them that do, but so they're taking those and then they're building a portable safe abstraction over them, and I think that's super powerful and cool. The flip side is back to what Jethro is saying. It's like LLVM doesn't properly support the flags needed for these instructions, so. Whenever possible, I prefer the intrinsics as well. Like the only other downside I've seen with them is we've run into various miscompilation bugs trying to use them. We ran into one in, I think it was the Poly 1305 crate. We had a AVX2 backend for that. And there was some really fun stuff involving like closures, runtime feature detection. Anyway, there's still an open issue about it. We managed to work around the problem by just getting rid of the closures. That totally fixed it. But they're a little bit worrisome if you try to mix, I would say, these architecture intrinsic wrappers and kind of fancy Rust code, right? You might run into a situation where things don't quite compose correctly and it just generates the wrong code.
Yeah, no, those are great points. Just scanning the chat, Nicola has made a very good point, which I just wanted to read through and wanted to get some of you, anyone to chime in on. It feels like inline assembly is a double-edged sword. On one side, we can start using it to work around the compiler now, but on the other hand, it risks killing the momentum to have support in the language compiler stack to write portable and safe. Please, if you wanted to clarify, Nicola, is it NAND or and maintainable, verifiable, etc.? If you wanted to clarify that, please do. Cryptographic code in Rust. It's a way to solve the problem, but maybe it's not the best way. And we've got a couple of, okay, so yes, thank you very much for the correction. What do we think about that? That's a very interesting point, right? It's like, it's good now, but is this the best way? Anyone feel free to chime in.
It's basically a last resort, but I feel like we've spent like years talking about some of these problems without like coming to a tractable solution. So, specifically if we're working around the fact that LLVM can't generate these ADX, MOLX instructions correctly, instead of like trying to use that, you can have sort of like little sections of code that do something like an at carry chain or something like that, that you write in assembly just for, these very specific kind of core operations. So I think like it's not something we want to like sprinkle everywhere. It's something where we want to have very specific applications for which, in the future, maybe this will all get sorted out. At such time that happens, hopefully it should be easy to rip out that inline assembly and just use the intrinsics when they start working.
Great, thank you. Hey, Lucas, how's it going? Great to have you as always. Please chime in.
Yeah, so I think, so that comment was made back when we were still on the constant time beat. So I think we need to sort of distinguish two uses of assembly. So one is assembly for, let's say, safety. where right now in the subtle crate, for example, they have to use an ad hoc black box where they make the compiler think that this part of the code can't be optimized, and inline assembly could provide a vector for black boxing that more effectively, because there would be an optimization barrier around that. The second thing is it would provide a means to implement the subtle crate more directly in a way that's less optimizable, because you'd replace the bitwise arithmetic with a direct C move, and the compiler would touch it even less, because now you'd have this optimization barrier around your conditional moves, and there'd be no, because in theory the compiler could see the bitwise stuff and realize that you're actually branching if it unravels everything. So that'd be a more robust way of doing that. And then the third thing is performance. And there's sort of two aspects to that. So there's access to instructions that dramatically speed up computation. So for example, if you're doing binary field arithmetic, you need carryless multiplication. And implementing it without this intrinsic is much slower, because you have to do basically the bitwise operations yourself. And you can't really parallel the performance unless you have access to the CPU instruction. And similar applications that are more common, for example, AES native instructions are also in this category, where if you have access to the intrinsic as a black box, you immediately speed up your code, but it's easily replaceable with a function call that knows what the intrinsic is about. And then you have performance on broader sections of code. For example, if you're implementing a finite field and you're adding two elements together, you need to do this add carry chain. And to do the chaining correctly, you need a larger segment of assembly code, and their intrinsics wouldn't work as well, because you need the compiler to be aware of the fact that your intrinsic is using flags, and it can actually replace the moving of bools around with a direct chain. So those are some categorizations that might be important.
I'd say specifically for carryless multiplication and for AES and I, the intrinsics are actually working really well there for us. In terms of those like add carry chains and that kind of thing, yeah, I mean, I imagine we're going to start experimenting with, you know, more coarser grained inline assembly that does a much more complex operation. And then maybe see if we can whittle down to just the wrappers and inspect what kind of code LLVM might generate with that. But since it's not aware of the flags, you know, I think it becomes very risky that you might run into a code gen bug trying to do that kind of thing. So it gets a little bit scary there. But yeah, I mean, some of these, the intrinsics do work really well, I think. So.
Great. Jeffro, did you want to come in? Yeah.
Yeah, let's see, there were so many things said already I wanted to respond to. Let's start with, yeah, intrinsics are working well for me for writing base 64, constant time base 64 encoder decoder. The question, the main thing I wanted to respond was that, yeah, I mean, obviously inline assembly is not the ideal solution. I don't think anyone has any illusions that it is, right? But it's a nice stopgap until you know, we've evolved programming languages far enough that things like constant time or zeroization or such, or like even specific compiler optimizations like the flags we talked about are actually implemented. Right, like even for create like subtle, right? I believe that in a lot of cases the generated code will be correct, right? If you analyze it, but I'm always worried that, you know, the compiler will get smarter and suddenly there's some optimization that you hadn't thought of before, and now your code is no longer constant time.
Yep. So yeah, I was talking to Chandler Carruth about that, and he was showing me some examples of like in future versions of LLVM, it's totally going to be able to see through the current black box. So yeah, that's where it would be nice to have like some sort of shared intrinsic for this sort of like data flow optimization barrier, which again is kind of a hack. It's just mostly trying to outsmart LLVM, but with an inline assembly, it will be possible to have one that's at least like slightly better than what's in Subtle today. And then, maybe it would be worth looking into kind of switching away from that model entirely to one that's more directly dependent on something like CMove. But then there are like performance considerations with that as well. So.
Yeah, Lucas, please chime in.
Yeah, so I've been thinking about this ever since we mentioned that, I think a few months ago. And I think a more durable solution would be to encode a subtle like API at the language level in Rust and in LLVM.
Yeah,
so then
that's the secret types, yeah.
But not necessarily secret types, because so I've seen a lot of focus on saying this specific type is secret, but you could get away with just doing secret bool as a minimal API and going from there. So basically replacing subtle choice type with sort of a secret bool, and then having the compiler be aware of that, because that takes care of most of the issues. The other thing is that like the other potential concern that would be left if you did that would be the compiler not being aware that memory accesses are not constant time, and like, for example, replacing like a constant time selection using the CMove to a logically equivalent accessing the index directly. But you could also sort of make more complex routines aware of the fact that there's this secret choice thing. So I think that would be more durable, but that would require LLVM support, because otherwise, no matter what Rust does to not touch this stuff, if LLVM just gets raw instructions, it's going to touch it again, which is a problem.
Yeah, the thing where, the compiler may just put things in memory where you were expecting things to only be in registers, right? That's kind of one of the things I mentioned where I'm like, yeah, I mean, compiler can just do something and it's no longer constant time.
Yeah, I think there are various ways you can easily screw up, like trying to do that sort of constant time selection thing, right? Like you could put in 2 addresses and try to CMove them, and then you access the address based on the CMove out. It only works if you are guaranteed that everything's in registers, right? So Subtle's API is actually kind of okay for that. Since it's constant time selection always builds a new value. But yeah, it's definitely tricky.
Yeah, no, there's some great points. I just wanted to share Nicholas Stradler's point from the chat to see what we all thought about this. So I doubt something like inner loop base field operation with the GitHub repo that they've shared here could ever be produced by the Rust compiler, as it is so specialized. Detailed use of existing register operations, memory lookups. Conversely, it would be nice to generate the assembly in a principled way, maybe via proc macros. Has anyone dived like deeper into the implementation?
Well, so regarding the proc macros thing, right? When the inline assembly was discussed, like how this should be done in Rust, one of the designs was to basically have a typed, but you could consider it like a typed implementation of every assembly language, right? Where there's really more of basically a compiler for the assembly, right? That understands, which instructions you're actually writing, what are the correct operands and things like that. And so this is what exists in the 32-bit Microsoft C compiler, right? It's really more integrated into the compiler than what we're doing now, which is basically just, oh, here's this string. I don't know exactly the main reason why we ended up going this way as opposed to that way, but I think some of the reasons could be, intrinsics are pretty much like that typed assembly language. So if you want that, you should use intrinsics, or maybe just too much work to implement the language. Those are two things that I think that have come up in that discussion.
Thank you. Hi, Nick. Hi, great to have you. If you wanted to share your points and maybe clarify anything that I may have said out there, but thank you for sharing. Thank you for coming on.
Hi, yeah, so I mean, what I'm trying to say is that I think maybe, you know, Rust is like a general purpose language, and there are various uses in as a specialized cryptography compiler. One thing is like the high level organization, making sure that secrets don't get revealed on a high level, but this is just like a specific kind of microcontroller thing, so it's maybe a bit niche, but you know, you have limited resources, and if you look at what this assembly does, it's like a combinatorial game of optimizing how often you need to like push a register and pull it back, and then when you run out of registers, what do you do? And so kind of getting, this is not my implementation, right? It's just like the fastest one I know of, which is which does two things. Like one of them is like, as written, it's like a huge blob of assembly instructions, which are hard to follow. So one thing is just expressing what's being done there, like in a more compact way, so you can actually grasp what's going on more easily. But the second thing is kind of solving this combinatorial problem of what is the optimal way to assemble these instructions to do the perfect output. So I was just thinking that maybe some of this stuff could be done in inline assembly, but using a crate which generates the code, like the code generation thing. I think this has been done before with Perl or whatever, like in the past.
Let me drop a link. So this is a kind of ancient abandoned project called the Deco that implemented, I think, the sort of general concept where you add this little const time attribute to your Rust code, which is effectively like a proc macro, and it then understands a subset of Rust and is able to kind of take that Rust code, parse it, and then do its own constant time architecture specific code gen based on that. So it's kind of
really good though, right?
Yeah. I mean, it's a really interesting idea, and something like this will now be kind of possible on stable.
Okay.
It sounds, yeah, it's like kind of an ambitious project, but you know, this one was abandoned. But I think it'd be really cool if someone were to like pick up something like this and try to.
I was just thinking that as well. So that might be added to maybe an issue opened or something like that. I mean, obviously it would be very incremental in what that means in terms of someone picking it up, but it would be great to even just blue sky think around that, like, hey, who would be up for that? Lucas, do you want to come in?
Yes, so what Nicholas was talking about reminded me of a project called Fiat Crypto. I think some people might have heard of it. So
well, if you're gonna attend the Rust formal verification interest group next week, you're gonna have a whole presentation on Fiat Crypto.
Yes. So basically, the gist of it was a common task in cryptography, especially public key cryptography, is implementing a finite field. For example, the code we just saw linked is the finite field for the finite prime field for the P256 curve, but other curves like curve 25519 need a different field. But the arithmetic is extremely similar, it just needs different constants. And so the idea with that project was to automatically generate a formally verified program in different languages that would implement the arithmetic. So you could easily have so actually the project can already generate Rust code, and
just drop a line.
I believe the Rust code it generates is already fairly optimized, and you could also have it generate inline assembly if that's deemed to be necessary. From my experience, I think actually Rust is pretty good at doing the kind of register allocation that you need for this stuff. Usually it's more so the tedium of implementing the multiplication in a loopless way. For example, if you look at like the way the Dalek crate does it, they just implement we need to multiply, we need to add these things together and these things together, etc. So yeah, I think on that front, Rust is actually relatively solid, but generating code would mainly save cryptographer effort.
I think
so do you know?
I think there's a continuum. Like the thing that's linked is like they actually implement the entire everything in assembly. So it's like so blazing fast, it's ridiculous. And there are certain situations where you just want to have the fastest thing. So I think fiat crypto is like an awesome project, but it's probably going to be quite fast, but it's not going to like go to all the way to the. It's a mathematical problem, right? What is the fastest way given a microprocessor you can implement something? So this is also kind of interesting, I find.
Yeah, I think Nicholas, especially with like M0 and M4, right? When you're thinking of like
M0 is just masochistic.
Yeah, they're just like, it's very nice to have like handwritten assembly, like well-optimized handwritten assembly implementations for those platforms that like, take into account the cost of like multiplies on like M0 versus M4 or something, right? We have in the Rust crypto project, we have a kind of M0 optimized backend for doing like Ghash, polyval. It's like finite field operation over like Galois field 128, right, to the 128. So yeah, when you're really wanting to optimize the hell out of something on an embedded platform, it's definitely nice to have a big, well-optimized assembly blob that does exactly what you want, right?
Yeah. Yeah, and I mean, the question is just with the thing that you link, like this deco, maybe it's possible to write it down in a way that's more parsable, more people, versus just lines and lines of single instruction assembly code.
So in a way, I see we go in full circle back to the approach that the Miracle library used many years ago. So they had a macro language for, well, it's all C macros, right? But you had a way to express specialized multipliers for some lengths. So you could pre-configure the library for a certain precision, and it would basically enroll these macros to get something close to handwritten assembly using the hybrid method, in which you kind of unroll the inner blocks of scolebook, so to maximize the register allocation. That would be like a nice trade-off between fully handwritten and fully, I don't know, compiler generated code with decent speed and portable to many architectures. Maybe we need to take a look at that approach back then, relying on inline assembly, and do it all over Rust. And then we get some decent middle ground.
I think this may be a place where like hackspec is interesting. Like if we could make hackspec the like Rust ESL, minimal Rust ESL that these compilers could support. Prajesh?
Yes, hi Prajesh. Sorry, excuse me. Sorry.
Yeah, hi, can you hear me?
Yes, we can. Yes.
Okay, awesome. Yeah, so we actually have so Arcworks is this library that I maintain for SNARKs, and in that we have a lot of elliptic and finite field arithmetic, and in there we do have sort of this kind of DSL, which is mostly focused around the multi-precision arithmetic that you need for finite field arithmetic. But yeah, it's basically like this set of macros which expand out into, which look like high-level stuff, like multiply, add no carry, stuff like that. But in the backend, they just expand out to one big blob of, in this case, still inline assembly, but it's not like it's chunks of inline assembly. It's just one big inline assembly blob, which has all of the which just carries out the entire multiplication routine at once. So I think this sort of macro-based cell type approach can be a good way to move forward.
Thank you very much for those points. Very, very much appreciated. So just before we start to wrap things up, what do we want to see next from inline assembly? What as feature, as a next step in implementation? What are some of the nice to haves that we would want from inline assembly as a feature? And anyone can chime in on that, please.
More portable intrinsics, less inline assembly.
Yeah, there are definitely a lot of reasons why you want intrinsics. Like the other one that's come up is MIRI support. So if you have intrinsics, you can potentially get those to work inside of MIRI. So they're talking about that. So you can use them in like const funds. So you can have const funds that are also fast. So that's cool. I would say the main thing I would love to just get out of inline assembly as a next step is somebody like Avani who works on the Rust compiler team confirming that inline assembly is a black box and that the LLVM optimizer will leave it alone. I'm pretty sure that's the case, but I would just like to get a yes, that's true from the Rust compiler team.
No, absolutely. And this will be a multiple part sync-up call. We're hoping to have part 2 of this with Amanu, and we'll frame it as partly an AMA with Amanu around this. And also he'll be sharing semi-presentational style, some of the history and the process as well. So we're hoping to have that on the next call. I mean, with it being the holidays coming up, the next call might be quite soon. So we'll work that out. And also Bas is going to be giving a talk on fiat crypto on the 29th of this month at the Rust Formal Verification Interest Group, which is the sister interest group to what we do here. And that's going to be a lot of fun. So he'll be presenting fiat crypto, Hackspec, and Concert as well. So it should be of interest to everyone here. Also, so if you want to take a look at a formal Ferris on Twitter, you'll see the same sort of Eventbrite link there where you can sign up for that event as well and attend that event, because this is an overlapping topic essentially. Great. So we still have a few minutes left. Are there any points that anyone wants to make, kind of like just to wrap up with where we were, with where we've come from with things? I want to also
can I say something?
Yes, please do.
So there is a cool thing, since you mentioned formal verification, there is a lot of effort to do formally verified assembly. So I see Jasmine mentioned, I believe there was that. But also
yes.
So there's several of these projects producing formally verified assembly that is proven under symbolic execution to be correct for a particular algorithm for all inputs, right? So, you know, sometimes we think of assembly as kind of scary and sketchy. When it's something like that, I think it's very interesting. I think maybe it would be cool if maybe on one of the future calls we could get someone from one of those projects to kind of talk about
I'll work on
project in
that.
general and how we could like integrate it in Rust. So
yeah, absolutely. I'll work on that as well. And Diego, you've mentioned Veil as well from the Evercrypt project, which has a huge library already. Do you want to expound on that a little bit?
No, it's on the same line as one Tony described. So it's a collection of formally verified assembly implementations for many primitives. I think the latest version, they have even a generic Biggin implementation, which is quite challenging for doing for arbitrary precision on Intel. But yeah, they're doing great work on that. And at least the benchmarking numbers on their papers are quite competitive with handwritten code. So it's a great alternative. If you're willing to spend some time on the, well, you can use the library as it is, but if you want to extend it with your own custom primitive, there is a lot of examples to take inspiration from, and you're willing to spend some time learning the proof assistant part of it to verify implementations.
That's really cool. That's really cool. That'd be something to check out and add into the mix as well. Tony, I saw you tweeted out an update to, I think, Biggin as well a few days back, or maybe it was
yeah, so the Rust Crypto project has a big cryptography oriented Biggin library, and we just cut another release. I mentioned earlier that const fun thing. So we wrote that library with the goal of being able to do a lot of kind of compile time arithmetic with const fun, to do things like pre-computing constants, pre-computing tables, constant tables. This is often done as like a build RS step today. So we're trying to get rid of that build RS step and just be able to do that all at compile time. But this gets very fun with inline assembly because you can't put inline assembly in consts. So it's kind of these features that you know, don't compose very well today. So this is where intrinsics are definitely preferable because intrinsics could potentially work in const fun. That'd be cool.
Amazing, amazing.
Did Pratyush have another question?
I think Pratyush, yes. Do you, or is it just you've got the hand up?
Oh, I just forgot to lower my hand from last
No,
time.
no worries, no worries at all. I've been there with that. So yes, just to wrap things up, thank you all very much for coming on this call. I know it's kind of like one of those Fridays, but thank you all for your contributions as well. I think there's a lot to kind of digest from this, and there's a lot to kind of follow up on. Like I mentioned, this is going to be a multiple part series of sync-up calls where we really grapple a lot more with this. And we will also discuss some other code gen issues with LLVM as well. So there's lots more to get into the new year. Again, with it being the holidays, I'm going to work out a time for early December just to get another call, possibly with Avenue up and kind of running, so that we can have a very good follow-up call to this whilst this is still prevalent in people's minds and before everyone checks out for the holidays, right? So I'll aim to do that as soon as possible. Also, please remember to follow the DevX initiative on Twitter if you aren't already, and check out all of the other stuff that we're doing. And please, 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 the Rust Formal Verification Interest Group, check out this month's event on the 29th. And again, that could even be a semi follow-up to even this call with everything that we've got going on. So Bass is going to be discussing a lot of things that we've already talked about here, and it makes sense for everybody's interests anyway. So thank you all again for coming. Everyone enjoy your weekend, and we'll see you at the next Rust Cryptography Interest Group Sync-up call. Thank you all very much, and have a good one.
Thanks, everyone.